Hello students, welcome to lecture 18 of your course Advanced Calculus and Special Functions. In this lecture related to Legendre polynomial, we will discuss some examples related to Rodriguez formula and expansion of a function fx in the series of Legendre polynomials, and a short exercise is given for your practice. Rodriguez formula we have already derived in the earlier lecture, and certain examples we have solved related to Rodriguez formula. So some new examples are here, but before that because in the special functions, these two functions also have special role. One is the beta function and the gamma function. The gamma function is denoted by this capital gamma n, and this beta function is bmn. Now the beta function can be defined by this integral 0 to 1, the limit is 0 to 1, x raised to power m minus n, and 1 minus x raised to power n minus 1 dx, and then you write beta mn. But this thing is also equal to 0 to 1 x raised to power n minus n, 1 minus x raised to power m minus 1 dx, and the condition is that here m and n must be greater than 0. So this is the formula of beta function. In fact, beta function is an integral from 0 to 1 where the power of x is m minus 1 and 1 minus x to the power n minus 1. So similarly, you can also write it like this. And there is a property that beta mn is equal to beta nm. That is why we are writing here x to power m minus 1, 1 minus x raised to power n minus 1, this the equal to x raised to power n minus 1, 1 minus x raised to power m minus 1. In fact, this is equal to beta nm. So beta mn and beta nm both are equal, and this is the definition of beta function. Then the definition of gamma function is this one. This type of integral gives you the value of gamma n, and this is the gamma function, x raised to power n minus 1 e raised to power minus x dx, and where n is greater than 0. You can also convert in another form. If you put in place of this x, you put x square, this it reduces to this form. So it is directly derivable from the first definition here. And we can also prove that gamma of 1 is 1. We have already discussed this concept in the lecture. And we can also derive gamma of 1 by 2 equal to under root of pi. So you can remember these standard results. Gamma of n plus 1 is equal to n into gamma n, and gamma of n plus 1 is also equal to n factorial, and this can be directly derived from property 5, and beta mn equal to beta nm, and this result also used in the complex analysis, that gamma n into gamma of 1 minus n is equal to pi over sine n pi. So this is an important result in beta and gamma functions. Then gamma of m is infinity, so that 1 by gamma m equal to 0 if m equal to 0 or a negative integer. If m is 0 or negative integer, then gamma m you get it infinity. And there is a relationship between beta and gamma function, and we have utilized this relationship in one of the example related to the Rodriguez formula in the last lecture, that beta mn is equal to gamma m into gamma n divided by gamma of m plus n. And one more important relation is there, that gamma of 2n is equal to 2 raised to power n minus 1 divided by under root pi into gamma n gamma of n plus 1 by 2. In fact, this relation in general is known as duplication formula. Duplication formula. So these are some important results related to beta and gamma functions, and these results can be utilized in the problems where we have to deal certain integrals. The next example related to Rodriguez formula, you can see I say that this is example 1. If x is greater than 1, then show that p n x less than p n plus 1 x. That means the Legendre polynomial of degree n, value of the Legendre polynomial of degree n is less than value of Legendre polynomial of degree n plus 1 for x greater than 1. So because here is an involvement of the natural numbers, n is the natural number here, so we can apply the principle of mathematical induction here. And you know, in the principle of mathematical induction, we prove a given result for n equal to sometimes 0 or 1 or 2, whatever is the feasible. We prove this general result for n equal to 0 or 1 or 2, whatever be the case, and then we assume for n equal to n minus 1, and then we prove it for n equal to n. So this is the procedure to solve a problem using principle of mathematical induction. So here we prove Pn x less than Pn plus 1x. Now since for x greater than 1, from Rodriguez formula we find that Pnx is greater than 0. From the Rodriguez formula it can be inferred that the value of Pnx is greater than 0 when x is greater than 1 for each value of n. Now by the principle of mathematical induction, we want to show that this is true for n equal to 0 or 1. Suppose I'm taking n equal to 0 here, so it becomes p naught 0 and it becomes p1x. In fact, p naught 0 and p1x. Is it true? I want to check it. Is it true? You know that p naught x is 1 and p1x is x. We have already computed these values. That means if I'm writing like this, that it means that 1 less than x, which is true by the given condition, because in the statement we are taking x is greater than 1, x is greater than 1, that means 1 is less than x, and that gives you p naught x less than p1x. So you can say that this result which we want to establish is true for n equal to 0, implies 1 is true. This result which we wanted to prove is true for n equal to 0. Now the inductive step, we assume that result is true for n equal to n minus 1. That means this is the inductive step. We want to show that it is true for n equal to n minus 1. In fact, here you are substituting n equal to n minus 1. So in right hand side it becomes n. So this is, you are assuming that this fact holds automatically. That means Pn minus 1 divided by Pn is less than 1. So I say that this is equation number 2. You want to establish this relation, means you want to prove this by utilizing this fact in equation number 2. Now from the recurrence relation 1, which we have discussed earlier, the 2n plus 1 x divided by n plus 1 equal to this quantity. Or you can, because you want to establish a relation between Pn and Pn plus 1. In fact, you have to show that Pn over Pn plus 1 is less than 1. Or you can, alternately, you can also show Pn plus 1 divided by Pn is greater than 1. So let us see. Here we are keeping Pn plus 1 over Pn on one side and other things on the other side. You know that this x, the statement we are given x is greater than 1. When x is greater than 1, this quantity, if I replace here with we are writing because x is greater than 1. So if I omit x from this place, and the another fact is that Pn minus 1 over Pn is less than 1, that is given in equation 2. So using these two facts, I can put here the sign of greater than in place of this, because you are this quantity if you are omitting, this quantity is less than 1. So in fact it becomes further smaller, and you are also removing this x here, so it becomes further smaller. That way you can write this quantity in left hand side becomes greater, so you can write this thing. Now after solving this, you get Pn plus 1 over Pn, and after simplifying this you get 1 in right hand side. So I can have Pn plus 1 divided by Pn greater than 1, so that I can say Pn from this I can say Pn less than Pn plus 1. Hence the result is true for n equal to result is true for n, whenever 1 is true for n minus 1, because you have considered that it is true for n minus 1, and in this step is called the inductive step. So in this way we have established the relation using the principle of mathematical induction. So we can say that for x greater than 1, Pnx, this Pnx is less than Pn plus 1 x. So this is proof of this result. Now here I say that this is example 2, the simple example here. Verify the Legendre polynomial P4x. You can find the value of P4x from the relation given earlier. P4x is this, satisfies the Legendre equation when parameter n is equal to 4. You know that the Legendre's equation, differential equation, is this, and we are using the parameter n equal to 4. So when you put n equal to 4 here in this equation, we get 1 minus x square y double dash minus 2x y dash plus, in fact when you are putting n equal to 4, so it becomes 4 into 4 plus 1 5, that is 20 y equal to 0. In fact, after putting n equal to 4, the Legendre equation reduces to this. We call it as equation number 1. Now you want to show that this P4 satisfies the Legendre equation, so you can consider that this P4 is equal to y. Then you find if it satisfies this equation, then you have to get the value of y double dash and y dash. So y dash is this and y double dash is this. Now substituting the value of y dash and y double dash in equation 1, so and after simplification here you can see that you will get 0 in the left hand side and in the right hand side. If you are putting value of y dash, y double dash and y in this equation here, so in after simplification in left hand side you will get 0 and right hand side is obviously 0, so 0 equal to 0. So from this you can say that P4x is the solution of 1. So that is what we wanted to establish. Next is the expansion of any function fx in a series of Legendre polynomials. You know, from certain you must have already. Okay, so in fact here we can find the expansion of any function fx in terms of in the powers or in terms of the Legendre polynomials. Suppose we assume that the expansion is summation r going from 0 to infinity cr prx1, where prx is the Legendre polynomial of degree r and cr is some coefficient. So we want to find this coefficient. This expression 1 can also be expressed in this form as going from 0 to infinity c of s psx. This is equation number 2. So where C0, C1, C2, CR are the constant which we need to determine. When we multiply both sides of equation 2 by PRX and then integrating it with respect to x from -1 to 1, we have -1 to 1. In fact, in the left hand side we are multiplying with PRX, so we are getting PRX and integrating from -1 to 1. The same fact is occurring in this side. But from the property of the orthogonal property, you know that this PR, PS, if both are equal, then we have some value. If they are unequal, the value comes out to be 0. We have already established in the earlier lecture. So here -1 to 1 is right here. This is 0 when r not equal to s, and this is equal to this when r equal to s. So in the summation in the right hand side, only one term will be left when r equal to s, otherwise all terms are 0. So when r equal to s, this becomes cr, and there is no term in the summation, only one term is left, because whenever r not equal to s, the thing is 0, otherwise it is 2o by 2r plus 1 if r equal to s. We have proved this result in the earlier lecture. Now using 4 in 3 equation 3 reduces to the form, this is left hand side minus 1 to 1 fx prx dx, and in the right hand side we are left with only one term, 2r 2 by 2r plus 1 whenever r equal to s, and cr will be the coefficient. So from here we can get the value of coefficient cr. So cr, you take this twice of 2 divided by 2r plus 1 on this side, so we get value of cr equal to this. So when you substitute the value of this value of cr in this expression are going from 0 to infinity, if you put this value of cr here and the prx is there, so this gives you the expansion of this function fx in terms of the Legendre polynomial. Now the example is here, example 1 regarding this. Suppose you have to expand this fx in the form this, where the value of fx is given to you. The value is 0 when x lies between minus 1 to 0, and value is 1 when x lies 0 to 1. In fact, we have broken this interval minus 1 to 1 in two parts. Whenever the value of x is from minus 1 to 0, the value of function is 0. When you take value of x from 0 to 1, the value of function is 1. So we have this function. Now we want to expand this fx in terms of the Legendre polynomial, that means in this form. The expansion in terms of Legendre polynomials is written like this, where the cr is equal to r plus 1 by 2 minus 1 to 1 fx and px. Now you break these limits of the integral in two parts, minus 1 to 0 and 0 to 1, minus 1 to 0 and 0 to 1 fx prx fx prx. In the interval minus 1 to 0, the value of function is 0. That means this thing is 0 in this part, so whole integral reduces to 0. Now in this part the value of function is 1, so here you can put 1. So that is why we are getting 1 into prx drx 0 to 1. So cr is in fact equal to 2r plus 1 by 2 integral 0 to 1 prx dx. Now from 1 we can have, by putting r equal to 0, 1, 2, etc. successively, c naught means 1 by 2, 0 to 1, r is 0 here, but p naught x is 1. You put here 1, 0 to 1, you simplify, this gives you 1 by 2. So value of c naught is 1 by 2. Similarly, c1 means you will put here 1, and p1x. P1x is x. P1x is 1. After simplification, the value of c1 comes out to be 3 by 4. Further, you get similar manner c2 is this, because p2 is this quantity, and after integration it gives you 0. Similarly, c3, you get here p3, the value is p3 is there. After simplification you get minus 17 by 16, and so on. Substituting these values in the expression, you have fx equal to this. So this is the expansion of that function in terms of the Legendre polynomial. So these are the exercises regarding the series expansion of this function fx in terms of Legendre polynomial, where value of fx are given like this. That's it about this lecture. Thank you.